For those of you that are actually going to be taking a stats class, these are some of the different types of calculations that you will need to do in that class. So it says determine the margin of error in a given poll, explain the meaning of the margin of error in a given poll, and calculate the number of poll respondents needed to give for a given margin of error. So with those three things, uh, when it comes to uh, doing a poll or asking people, like, say, do you approve of this or that? Are you going to vote for this person or that person or whatever it takes? A couple of the really weird things that we need to make sure we understand here are that so when we start doing these polls, one, and assuming you want to do the poll well, as opposed to say something you see on like Fox News or something like that. One, you have to make sure that the respondents are similar to the population. Two, you have to make sure that the responses are independent. And then I'm sure there's other stuff, but if you can't do those first two things, don't bother doing anything with your poll because it's obvious or it's going to be total trash. And then another thing that we're going to come up with is uh, if you want more accuracy in your poll, you need more people. So if we're talking about number one, respondents are similar to the population. This means that the people that you're talking to actually represent the population. Uh, you can't always do that. So there are some ways you can go about trying to make corrections for that. Just as an example, like say in the Metro Detroit area, about 70% of the population is white, 20% black, and about 10% Latino and other ethnicities. If you go and you start cold calling people, do you really think you're going to get 70% of the respondents being white people, 20% being black, 10% being Latino and other ethnicities? Highly doubtful. Are you going to get all the different ages of people that are actually representative of that population? How many of you get a phone call where it says spam risk, or you look at it and go, I don't know that phone number, answer. Right. Whereas you call my dad, he's going to talk with you. Even when it says spam risk, you an idiot, don't pick up. Telephone can't tell me what to do. Hello? Oh, and a lesson that my dad learned the hard way, and he still didn't learn it the second and the third time he did it. When you get one of those people calling you, don't start yelling at them because then they can start spoofing your number. So your number's the one that comes up when they start calling other people, and then stupid people that don't know about that will start calling you and telling you, stop calling me. My dad still picks up the phone because they called. I have to talk with them. No, you don't, Dad. No, you don't. But anyway, I'll suppose for a moment that we know that, say, 30% of the population in a given area is people under the age of, say, 40 years old or something like that. And when you look at the responses that you get, you've only got, say, 10% of the people that you talk to are 40 years old or younger in that area. You can try to make up for that by saying each one of those, the 10% of people that you did talk to, each one of them now represents, say, three people to boost your numbers up to about 30%. But then you still have to make sure that the opinions of the 10% of the people that you talk to are actually representative of the population. And again, let's be honest, if someone calls you out of the blue, it's like, hey, you want to talk politics? Anyone can be like, yeah, sure, let's do this with the stranger. And depending on the types of questions that they actually ask you, um, sometimes they can try giving you a survey. And depending on the people that are paying for that survey, they can ask some really stupid questions. Uh, like the last time I actually picked up for one of those phone calls, the person on the other end, it was when Obama was running for president. Would you vote for Obama if you knew that he was a dirty Muslim? Wait, what did you just say? F off, mother. Haven't talked to anyone since. So they're they can try to sway you uh, with polls and with surveys as well, depending on the way questions are asked. They can actually lead you to the responses that they want. If you ever take a really well-written survey, you're going to find it to be annoying as all hell. How much do you love this product on a scale of 1 to 10? Then the next one is, how much do you like this product on a scale of 1 to 10? How much do you dislike this product on a scale of 1 to 10? And part of the reason they will ask you literally the same question three different ways is to make sure that you're not just sitting there going 10, 10, 10, 10. Because if I ask you how much do you love this product on a scale of 1 to 10, 1 is horrible, 10 is great. You rate it a 10. Then I ask you how much do you dislike this product on a scale of 1 to 10. 1 is a whole lot, 10 or 1 is I don't agree at all, and 10 is I totally agree or something like that. And you choose 10 again, you just said, I love this product, it's wonderful. I hate the whole thing. What? So you also have to make sure that the responses are independent. Uh, I'm sure we've all remember peer pressure. If you're with, say, 10 of your friends and someone's doing a poll and they ask all 10 of you at the same time, like, say, who are you going to vote for? If you're not going to vote for the same person as, say, 8 of your 10 other friends, are you going to be the one that says, yeah, I'm voting for the other person? Are you just going to say, yeah, I'll vote with whatever my friends are, just so I don't have to put up with their crap while we're having lunch or whatever? Most people are going to lie in a situation like that. So even though they just talked to 10 people because the 10 recorded votes weren't independent of each other, they should actually only count as one. And then the more accurate you want, the more people you're going to have. When I was teaching a class like this several years ago, one of my students was actually working with someone who was running for Congress. I don't remember the state Congress or U.S. Congress. Um, and he wanted to do a poll in his area where the margin there, which is what we're going to be talking about, was going to be less than 1%. You can think of the margin of error as, say, the expected range of values we should be getting. What's going to happen is, like, if I gave every single one of you an assignment to do, like walk up to 50 people or walk up to 100 people and ask them, do you like peanut butter and jelly sandwiches? Yes, or you're allergic. The number of people that say yes for each one of you is going to be different. They should all be fairly close. But no one's gonna have exactly the same values. So out of 100 people, you might find that one person might find that 70% of the people said yes. Someone might find 72, one might find 69, 67, 84, 56, something like that going on. So the more, when you look at all those numbers, we can then take them and try to figure out, okay, what is the quote unquote true proportion of the population that likes peanut butter jelly sandwiches. So you can, the more accurate you want that number to be, the more people you need to talk with, the more people you need to talk with, the more expensive things get. And what ended up happening with this particular congressman, because they wanted a 1% margin of error, it basically came down to uh, he would need to talk to 250 to 300,000 people, but there are only like 30,000 people in his district. And not all 30,000 people are of voting age. So these numbers can get to be a little bit weird. But another weird thing that happens is we want to have a 1% margin of error. Uh, it doesn't matter if we're talking about, say, who's going to win, uh, like president of student government. It doesn't matter if it's who's going to win, like say mayor of Royal Oak or whatever city you live in. It doesn't matter if we're talking about who's going to win the governor of a particular state or the entire country. It's the same number. And when you start looking at larger populations, so if we're talking about, say, the president of the United States, we probably need to talk. And you wanted a 1%, it'd be, let's say, 200,000 people. That's 200,000 people throughout the entire country. You have to make sure that the respondents that you're talking to are representative or similar to the population that you're dealing with, and that the responses you get are independent. So a lot of stuff going on there. And with that margin of error, the formula for it. The formula is going to look really, really scary for a moment. Turns out to be z squared PQ divided by MOE squared is equal to N. N is the number of people that you need. And anytime you're doing a calculation for N, the number that you get there is the minimum. So if you get, say, N equals 600, you need to talk with 600 people. If you get 600.0001, you need to round that up, because 600.0001 would be the minimum. If you only talk with 600, you have less than the minimum to need that one extra person. With the numbers that we have here, if we're doing a poll or you're doing a survey or something like that, and you're trying to figure out how many people you need, if you have no clue at all, you can use something called the worst case scenario. And this basically means that P is equal to Q is equal to 0.5. So what we have is P plus Q equals 1. So this basically means you've got a 50-50 chance. If there's, say, a poll that was already done by someone else that says 70% of the people like you or are voting for whatever, you can then come back and say, well, what if it's 70% for, 30% against? plug those numbers in, and you will get a smaller sample size that you need. Z is approximately 2.0. If you look it up, at least most of the time it's 2.0. There is an actual table you can look at to try to figure all this stuff out. A lot of times in science, we talk about a 95% confidence interval. So we want that 95% confidence level there. That z-score is actually going to be 1.96. What's 1.96 out to 10 decimals? Go. Anyone? Exactly. What's 2 squared? What's 2 squared out to 10 decimals? Still 4, right? The nice thing about this, 0.5 times 0.5 is 0.25. 0.25 times 4 is 1. Which means to get a fairly decent approximation here, you end up with a 1 divided by margin of error squared is equal to n. Doesn't that look so much nicer? And when you've got this, or you could even do it as something like that, which basically means no matter how you put this into the calculator, as long as you hit the right buttons, you're going to get the right answer. Now that margin of error, that's the amount of accuracy that you want to get. A lot of times, if you see polls that are done nationally, you'll see that certain person has, say, 52% of the vote, plus or minus 3%, or plus or minus 5%. That 3% or 5% is that margin of error. So if we try to do a couple calculations really quickly, none of these are too difficult. So if we literally do say 1 divided by 0.05 and square it like that, you can see that we get about 400. So what that means is if you are willing to have your margin of error be plus or minus 5%, you can talk to as few as 400 people and essentially know what the answer is going to be. If it's going to be a particularly tight range, 0.05 might not be good enough. Like I said, a lot of the polls that are out there will do it to 3%. So you can see what happens in this case. And again, these numbers here, this isn't saying, oh, we're going to be doing this for, say, city council. This could literally be, let's try to figure out who's going to win presidency of the United States of America. You can find 400 people that adequately represent the entire population. That's all you need. At 3%, you can see that it comes out to be 1,111.111111. That kind of tells you that we need to round up. So you'd actually have to talk with 1,112 people. So no matter what the decimal is here, we always round up. For the person that I was talking about, they wanted like 1%. What does this come out to be, like 10,000, something like that? Yeah. So 10,000 people. We can actually make it a bit smaller than that. But again, 10,000 people, it doesn't matter if we're talking about who's gonna win, uh, uh, like get on student council at OCC, who's gonna get be the mayor of whatever city you live in, 10,000 people, even if it's president of the United States. And one of the big issues that comes up with something like this, how many of you live in a city that has less than 10,000 people, or maybe has 12,000 people, 15,000 people? No one's from like Oak Park or Hazel Park, Pleasant Ridge, Center, or you know, Lathrop Village, I should say, Beverly Hills. No, okay. So, let's say you have a city that is 15,000 people. What percentage of those people are actually of voting age? Uh, so it is actually possible that when you, with some of these numbers, depending on the accuracy that you want to get, you can end up with, uh, like again, if you're looking to be, say, mayor, Pleasant Ridge, how many thousand people live there? 3, 4? So you'd have to talk with every single person 2 to 3 times, and that includes 1-year-olds and 2-year-olds. So, can a 2-year-old vote? No. So, according to this, you still need to talk with 10,000 people, but there might only be 2,000 people you can talk to total. So we do have to be worried about that sort of thing if we want to make this really, really accurate. So plus or minus literally 0.5%. Now it's up to 40,000 people. And like I was saying, with these, if I open the parentheses here, say 1 divided by, say 0.01, close the parentheses, then square that whole thing, you get the same answer. So like what I've got here, thing on top, what I've got here is the thing down here, and you get the same answer. So don't be happy about that. This means if you put the numbers wrong, you can still get the right answer. Yay, right? It's a win for everyone. So let's get back to so we've talked about pie charts before, right? Hey, can you make a pie chart? No. That's the only correct answer. No, and neither should you. So you can see here where it says the margin of error for a poll is a statistical measure that provides a range of values that the true outcome of the poll is likely to be inside. So what, again, what does that mean? It's a range of values. You will never know exactly what the true value is out to 15, 20, 30, 50 decimal places. Most of the time, you don't need a calculation out to that many decimal places either. So the margin of error is just telling you, we expect the numbers to be somewhere between here and there. So you can see where it's saying, a lot of times margin of error is going to be plus or minus 3%, which means if you have a particular political candidate who's, say, polling at about 52%, plus and minus 3%, they could capture anywhere between, say, 49% to say 55% of the final vote. If we're talking about something like this, though, what I guess another thing that I should mention here is with these calculations here and with these calculations here, we're assuming that you've only got, say, two candidates. If you have five or six, uh, these types of calculations just got a whole lot more difficult to do. But still, you can uh, end up trying to do something similar to that. But instead of, say, hoping that you get, say, 50% or more, you might even be able to get as low as 45% of the vote and still win, because some of those other candidates, other than, say, your main competitor or whoever it's going to be, might actually still uh, take up a percent or two of the vote. But looking at what we have there, assuming that it's only two candidates, one of the candidates gets 49% to, so 49% to, say, 49.99%. Did they win or did they lose? They're gonna end up losing in that case. So even though at, say, 52%, they look like they're in the lead, because of that margin of error, that can be uh, that they could be in the lead, but because of the margin of error, they could still actually end up losing. And one of the better things that I've actually seen when taking a poll is typically, say, the margin of error is going to be about 3%. But what's something else that might not be taken into account if we assume that there's going to be two candidates and you're performing a poll? Let's say you're limited to two candidates, so candidate A or candidate B. Are you going to vote for the library renewal, whatever? Are you going to vote for or against the uh, millage renewal for whatever school system you live in? What's another thing that you need to be worried about, maybe take into consideration? But the last election out of their mind and just forget about everything. Well, what's another thing that can happen? How many people are going to be like, I don't know. So the margin of error, and this is 3% basically from stats, and then margin of error, whatever percentage it is, from all the people that are undecided. When you when you start looking at a lot of the poll numbers and a lot of the things that are coming out, um, especially with like the last three elections, you've got the margin of error. You've got a certain number of people that are undecided, and for reasons like we're talking down here, just because your candidate's in the lead does not mean that they're actually going to win. It's just that there's they're fairly likely to win. It's not guaranteed. When you listen to people talk about what happened after the election, everyone's trying to come up with the different excuses, and the pollsters are wrong. They don't know what they're doing. Blah blah blah. But then you look at the numbers, and what was Harris polling in Michigan before the election? Like 51, 52%. What was her final vote tally? Somewhere in the 49 or 48%, which means the pollsters actually got it right. It's the political commentators who have no clue what the hell they're talking about. So when you take into consideration the 3% from the margin of error that comes from stats plus all the undecideds, you might actually end up with, say, plus or minus 10%, plus or minus 15%, something like that. So, just looking at it, it's coming down here, it says an Associated Press poll indicated that 63% of teachers below college level feel like the amount of homework students give is not excessive. The poll has a margin of error of 3.5%. With a 95% confidence level. Write a sentence or two explaining the results. What do you think that means? So it says 63% of teachers don't think the amount of homework they do is excessive. What what do you think that actually means? Put the plus or minus 3% on there, or 3.5%. Could be anywhere between 59.5 to what, 66.5% of teachers basically don't know what the hell they're doing when it comes to homework in high school. Is that fair to say, or am I overstepping bounds? Any of you ever think that your teachers gave you way too much homework? You ever look at some of your teachers in high school and you're like, I've got 6 classes this semester. Yours isn't the only one that I've got. Right? If you're in college, can you choose to take, say, 1 or 2 classes per semester? Yeah. And if you're going to be taking a class where it's known that they're going to have a whole lot of homework for you or a lot of busy work for you, that you can try to take that in, say, a semester where you take some lighter classes, right? But when you actually get into like homework, and for those of you that are looking at, say, psychology or sociology, something like that, there's an area called human factors. You get into some of the research in there and you look at the way that a lot of teaching is done, and you compare that to what the research says, and you realize that quite often what's been going on with teaching for decades is not beneficial, has never been beneficial, does not work the way that they think it does. Because just think about how many of you have ever done all your homework, did really poorly, and then your teacher or your professor tells you should do your homework. Like, well, I already did it. It's actually something that happened in one of my college classes. Students that were taking the class for a third time were averaging a 70% on exams. And for those of us taking it the first and second time, we're averaging a 30% on the exams. And that was after we all got a 10% bonus for actually doing the homework. And then the professor would yell at us, you need to do your homework. And I actually called them out and said, what do you call that on the front table? Who said that? Uh, he also tended to teach a class where you have 120 students at the beginning of the year. By the final exam, there are 20, and it's the student's fault they can't handle it, not his fault that he's a piss poor professor. So, anyway, with homework, stuff like that, uh, giving good homework problems is useful. Uh, Giving a lot of homework problems like they used to do, uh, where you just come up with um, or where you just like, I want you to do problems 1 through 151 odd in the back of the book and get it done by tomorrow. We get right on it, right? So formula for actually computing the margin of error. That looks scary at all? So again, P is the proportion of people that are say for whatever it is you're looking at. 1 minus P is the people that are against it. If you're using someone else's survey results, you can plug in their numbers in here. If you are using or if you don't have any survey results, then you have to use the worst case scenario, which would be 0.5 and 0.5. Then you can see how the primary varies a little too. If you rearrange this whole thing, it turns into this equation. Or try to figure out how many people do you actually need to talk to. Anybody want to go through the math to show how that works? Yes or no? How do you get rid of the square root? What's the opposite of the square root? Well, we'll take a multiply. So the square root is square. So you square that, which means you're going to square that, which means you're going to square the margin of error. What's 2 squared? Or that 2 is the same thing as this z that's out here. MLE squared, margin of error squared. Basically, you square both sides and then you swap margin of error and make it easy on yourself. So here they're trying to get you to go back and try to figure out how many people do you need to actually talk with in order to do this. See if there's anything else in here. So if we want to try to do different categories, I can actually use the graphing calculator. I can go to stat and edit. And again, oops, clear this stuff out, clear this stuff out. And let's say L1 is going to be my margin of error. So I want to look at say 0.05. Let's say 0.01. And oops, that should be 0.05. Now over here, let's say the probability or the chances that someone's going to vote for you is 0.5. We'll do 0.25, 0.75, and then let's say 0.1. We'll do these same numbers for everything here. So 0.5, 0.25, 0.75. And then 0.1. So what is the formula that we're going to be using here? So if this is the formula here, z is going to be approximately 2. So 2 squared. I'm going to have 4 times second and then L2 times second, and using the formula that was in the textbook, this is going to be, oops, not quite that, going to be 1 minus whatever's in L2 divided by L1. And then we square that. And we get some of the same numbers that we did before. And if you look at these numbers again, when we're talking about them, we have to make sure that no matter what value comes out here, if there is a decimal, you're always going to bump it up, okay? And one of the things that you should notice here is that 50-50, if we think your candidate or your whatever it is you're voting for is either 25% likely to pass or 75% likely to pass, you get exactly the same numbers. If you think that your whatever it is 90% likely to pass or 10% likely to pass, again, you get the exact same numbers. Why is that? With the formula, that we have, it says P times Q. If I ask you, what is 2 times 3? You say 6. If I say, or ask you, what is a 3 times 2? You're like, it's the same thing, you idiot, right? So for multiplying, does it matter what number comes first and what number comes second? Absolutely not. What matters are the numbers that you put in there. So if we were to draw a little bit of a graph for, say, what this function looks like. We can have our proportion down here, the number of samples that we want here. And I'm going to call this right here in the middle 50%. The number actually goes up, hits a peak, like right at 50%, and then comes back down. So if this is 0%, this is 100%. So when I was saying if you don't know what numbers to put in there, use the worst case scenario. Which because of the what's going on here, it's always going to be 50%. So you can look at that. And like I said, if you know that someone else has done a poll, you can definitely use their numbers, but most of the time, just thinking about yourself, and let's say you're looking at a poll and the political candidate you want to win, according to their poll, is losing, do you instantly believe that your candidate is losing? Or do you, and I'm not saying who you're voting for or anything like that, just keep that stuff to yourself. Just, do you instantly believe that your candidate could be a loser? No, absolutely not. No one wants to believe that. So what are a lot of these political candidates going to do? They're just going to come out and assume that whatever poll it wasn't done that well, or that they can do it better. Even if the poll was done by a professional organization that's been doing this stuff for, I don't know, 150 years, how much experience do they have and how much mathematical skill do they have? Probably little to none, but that they're still going to be thinking, yeah, I can do this better than they can. No, you can't. But just again, something to think about. We can do the same types of calculations in Excel, and you can see in the little snippet that's down here, they're assuming there's a 32% chance of someone winning or something passing. Then look at the different margins of error. So 1% is 8,704 people. At 4% margin of error, it's 544. So the less accurate your poll is, the fewer people you actually have to go and talk to. And depending on what's actually going on, you may well, you may or may not be able to actually use the results from the data that you've already collected. So you could look at that or look at some of the calculations we did and say, you mean I need to talk to 10,000 people? I can afford to talk with 10,000 people. Do you ever see the people that are like out there trying to get you to sign a petition or whatever to get something on the ballot or to get a person on the ballot? A lot. And this is something that's come up quite a few times on the last couple of years. I think once for governor, a lot of the several candidates for governor on the Republican side use the same company. Every signature, that person gets $1. So is there kind of incentive for those people to start making up names and addresses and signing things? So if you need to talk with 10,000 people and it's going to cost you $1 a piece, that's $10,000. If your political campaign has $2 or $3 million, that's nothing. If you're running for, say, city council or something like that, $10,000 might be your entire budget for running for city council or for mayor or whatever it happens to be. So you have to watch out for that. Stuff that we've got here. So it says here use direct variation equations, and somewhere in here there should be a indirect variation equations. So direct variation versus indirect variation. What you see down here is direct. What you see down here is actually what would be called indirect. And we've gone through how to make scatter plots. We've gone through how to plot some of the stuff. But it says here for the equation y equals 200 divided by x, fill in the table of values. So when x is equal to 1, 200 divided by 1, 200. X is equal to 5, 200 divided by 5 is 40. So you can see that this is already filled out. And then you can see the little scatter plot that we've got here. Now, looking at this particular type of equation, though, what does 200 represent? Oh, wait, we don't care, do we? Something that's highly related to that we might actually care more about. And I believe this is some of the stuff that comes up on the some of the online homework problems in here. We have an equation, speed, or if we're talking about if it's in a straight line, we can call it velocity. What are the units of speed? What's your speedometer say? What are the units for that? Mm-hmm. So it's distance divided by time. Now, what if I want to rearrange this so I can figure out how long it's going to take me to get somewhere, right? Looking at the original equation here, I can literally just swap these two things. So I can do distance divided by speed. Why is something like this kind of important? Talking a little bit about it last time at the end of class. Let's say I'm running 2 minutes late to class. I live 5 miles away. So I'm saying distance equals 5. Uh, and let's say on a normal day, takes me 10 minutes to go from my house to here. I want to, I can look at different speeds and see what that's going to be. So distance 5 miles in 10 minutes. We're used to miles per hour. So I've got minutes here. So minutes will cancel out. 5 times 600 is 300 divided by 10 miles per hour. Cancel that out. So my normal traveling time here is, or traveling speed is about 30 miles an hour. Does that seem reasonable? So that's the average speed for the residential street that I live on. The average speed for the main roads that I drive on. The average speed for the expressway that I take, plus the amount of time I have to stop at all the different traffic lights. And sometimes have to wait behind someone who wants to make a right turn but doesn't want to make a right turn because there's no sign that says you're allowed to make a right turn on red. So they just sit there for 3 minutes straight. All of that is eating into the travel time or the amount of time it takes me to get here. Now, let's say I'm running a little bit late and I need to save, say 2 minutes or 3 minutes. So I can go back. The distance is still going to be the same. But let's say I need to do it in 8 minutes. What speed do I need to go at? So again, it's going to be 5 miles in 8 minutes. Same thing going on here. 60 minutes per hour. The units of minutes will cancel out. 5 times 60. 300 miles in 8 hours. Not as easy to deal with as before, but we can still do 300 divided by 8. So we get 37.5 miles per hour. Okay. Now, let's say I'm running really late. And I need to save 5 minutes. So my travel here has to be 5 minutes, not 10 minutes. How fast do I need to go? What happens is going from 10 minutes to make the trip to 5 minutes to make the trip. I cut the time in half, so my speed has to double. So I now have to average 60 miles an hour, which means, again, 60 miles an hour, driving down the residential streets, driving down the surface streets, driving on the expressway. On the expressway, is it easy enough to get up to 60 miles an hour? Anyone here actually drives 60 miles an hour on the expressway? You do, how many people get right up on you and start honking and yelling at you and all that? So definitely 60 miles an hour on the expressway. Totally safe, totally fine. But 60 miles an hour down a residential street. Anyone ever try to drive that fast on the residential street? Yeah. So can't do that. If we say cut the amount of time it's going to take me from 10 minutes, so from 10 minutes to 5 minutes, we double that speed. 60. From 5 minutes to 2.5 minutes. So again, we cut that time in half. We again have to double that previous speed, meaning I'd have to drive at 120 miles an hour on average from my house to here to make it in 2.5 minutes. Does that sound safe at all, even if you are on the expressway? Right. So basically what I'm trying to say here is, uh, if you're running a couple of minutes late, can you go a little bit faster than you normally would, or a little bit faster than average, to try to make up some of that time? Yeah. But make sure, one, you do it safely, and two, at some point, there is no amount of speeding you can do on the highway and surface streets that'll make up the amount of time that you need. So watch out for that. Another thing that comes up, another thing where we can use something like this. I'm actually going to do this with Excel. So if I know, make this as big as possible too. So distance I want to travel, and we're going to look at different speeds and how that affects time. So speed and then time. So let's do this in increments of say 5 miles an hour. Hopefully. Yay. Excel realizes that I'm going by or incrementing this by 5 miles an hour. So great. So again, if I'm doing like the drive that I have tomorrow, 100 miles from my house to Saginaw, what's the formula that we have? It's equal to so the amount of time it's going to take me is distance divided by speed. So I have to look at distance, divide that by the speed. And the time that I have here is based on the units of time I have for speed. So if it's 5 miles an hour, it's going to take me 20 hours to get there. Clearly, I'm not going to be walking or jogging to Saginaw in the morning. And again, because I want to continuously reference this 100 right here, I can put up here $B, $1. Now I can take that and drag it down. So if I drive at an average of 50 miles an hour, and I think we all know that from here to Saginaw you have, what's it called? I-75. Do you think you can drive faster than 50 miles an hour for most of the way on I-75? Except for when it's snowing. So looking at everything that we've got here, these are all in units of hours. So this is telling me that if I drive essentially an average of 70 miles an hour, which on the expressway, what's the speed limit on I-75? 70 miles an hour. I can get there in 1.428571 hours. How long is that? Anyone? Exactly. So can say here time in hours, and then come over here and say time in minutes. So whatever the time is in hours times 60 minutes per hour can drag all that down. I can highlight all of these values here. And I'm going to format the cell. Number, we'll do it out to, we could actually do it out to 0 decimal places. So if I drive at 60 miles an hour the whole way, it's going to take me 100 minutes. 65 miles an hour, it's going to take me 92 minutes. 92 minutes is approximately what? Hour and a half. If I drive at 70 miles an hour, I can get there in 86 minutes. If I drive at 80 miles an hour, I can get there in 75 minutes. So what happens if, say, I'm driving and I got a late start and I need to make up, say, 20 or 25 minutes? Is that safe driving speed, even if it is on the expressway? 2, can I actually do it? So if we assume that on a normal day, it's going to take 86 minutes for me to get there. Well, let's say I'm running 12 minutes behind. How much faster do I have to go? See if I take these and drag this out a little bit further. So 86 minutes, and I don't know, let's say that I actually need to save 15 minutes or something like that. Means if I drive the entire way up there at 85 miles an hour, I can save myself 15 minutes of travel time. Is 85 miles an hour a safe driving speed on the expressway? And again, you have to keep in mind that this is the average traveling speed. So all the time I spend at traffic lights waiting for the idiot ahead of me to make a right turn, that just means I need to go even faster on the expressway to make up for that lost time. So just looking at what we have here, is there any way that I can really uh, say make up for lost time? If I do a little bit of speeding, yes. Is there any way that I can make up a whole lot of time if I do speed a lot of speeding? Let me check that out. If I drive at 100 miles an hour, I can make it there in an hour. And again, that's an average of 100 miles an hour. And I'm sure the state troopers, all 5 or 6 of them that I pass by, are good. Oh, hey, we know that vehicle. He's heading off to his math class. He's okay, right? Yeah, right. So we can look at this. We can actually come in and try to graph it too. So highlight everything, insert scatter plot, scatter plot. So there is my scatter plot. And again, out here are the number of hours that it takes me. And down here is the speed that I need to go at. So if I'm going from 5 miles an hour to 10 miles an hour, I doubled the speed. So I cut the amount of time it's going to take me to get there in half. Going from 10 miles an hour to 20 miles an hour. Again, I doubled the speed. So I cut that original value that I had in half. 20 miles an hour. So you can kind of see it on here. It says 20 miles an hour, 5 hours. If I bring that up to 40 miles an hour, 2.5 hours. If I go 80 miles an hour, how long is it going to take me? Half of the 2.5. What's half of 2.5? 1.25. So be about 75 minutes. So thing that we need to keep in mind when we're looking at all of these, again, is can you do something where you drive, the faster you drive, can you make up for some of the lost time if you're got a late start? Yeah. Can you make up for a whole lot of time? Like, let's say I ran half an hour late. Yeah, that's not gonna happen. And let's say instead of 100 miles, let's say I want to do this at 250 miles. So 250 miles, if I'm gonna go at 5 miles an hour, it's gonna take me 50 hours to get there. Uh, double the speed, cut my travel time in half, double the speed again, cut my travel time in half, double the speed again, cut my travel time in half, double the speed again, cut my travel time in half. So if I'm going to be driving, say 250 miles, and most of it's going to be expressway. If I do 70, it'll take me 214 minutes to get there. If I do 80, it takes me 188 minutes to get there. How much time did I just save by going an extra 10 miles an hour on the expressway? Well, that minus that. 10 miles an hour faster on the expressway and it saves you about half an hour. Does that sound like a good trade-off? Maybe, maybe not. What are, again, looking at the numbers there, if you can save 27 minutes on a trip that's gonna be that long, is it gonna be worth it to go a little bit faster? Is 80 miles an hour that much less safe than say 70 miles an hour? Not really. Um, I believe it's you turn a number back to my days in physics. I think it was if you run into say a brick wall and without destroying the brick wall, so you just come to a sudden stop. It's at 50 miles an hour or 60 or 70 or 80 or 90. You're dead anyways. So might as well get there faster, eh? What are some other considerations that you should take into account whether or not you can actually do 80 miles an hour safely? What do you think?
Is that getting pulled over?
Well, not necessarily getting pulled over, but I've seen like people that are driving a Corvette or Camaro or I think I saw a couple Lamborghinis a while back. Can the Lamborghini easily do 80 miles an hour and do it safely? At least I hope so. And a smart car. Have you ever seen one of those? You take whatever car you have, you basically cut it in half, and then you put the rear wheels behind your back seat. That's a smart car. Put a lawnmower engine in it. Do you think you can do 80 safely in one of those? No. Um, if you got brand new tires, brand new brakes, collision avoidance system and all that sort of stuff, does that make it safer than if, say, you're in a older piece of crap car with the really bad brakes and balding tires, bad shocks and all that sort of stuff? Yeah. If it's a nice sunny day versus snowing, that's another thing we need to be worried about, right? How much other traffic is on the road? Does that matter? So can you do in general, can you do 80 safely on an expressway? Uh, will the cops pull you over if you're doing 80? Maybe. Uh, but what's a way that you can avoid getting pulled over by the cops if you're speeding on the expressway? No, now do I have everyone's attention? What do you think you need to do? And this is to avoid getting a ticket. Not talking your way out of a ticket to avoid getting pulled over in the first place. What do you need to do? I'm sure there's someone else going faster than you. I'm actually serious about that. Uh, Many years ago, I was uh dating someone who lived in Allen Park. Has anyone ever been down there before? On Southfield, the freeway through Allen Park, the speed limit is 55. The Allen Park police take that speed limit very, very seriously. If you know that and you know where they tend to hide, any on Southfield, anytime that you're going to go under like a or pass by a major road, you tend to go under, which means you go down and then you have to come back up again. As you're coming up, there's going to be one of the officers right there. So if you know that, you you go under, you come up, you look over, okay, there's no cop there, you can go a little bit faster. But then as you're going to be going under, you slow down, then you come up on the other side. If there is a cop there, you're thankful that you slowed down. If there's no cop there, it's, I can go a little bit faster. But some people don't know that, so you slow down going underneath it. And people behind you get really, really antsy. So you just let them move over. They go through at 70, cop gets them. Since the cop's already busy, I don't have to worry about the speed limit anymore. If you're gonna do, if you're driving down Southfield through Detroit, what's the speed limit? Anyone know that one? Posted is 55. What's the real speed limit? I actually had a cop get right up on me, turn on his lights. I was doing 80. He just wanted me to get the hell out of the way. And as he passed me by, like, all right, I'll take that from an officer over a ticket any day. 80 to 55, that's what, 25 over. That's major points, probably loss of license, blah, blah, blah. You don't have to give me a finger for that. I'm totally fine with that. I'm not going to worry about that. So anyway, just a couple more like quick things on this sort of thing. Looking at the data, the way that it's being shown here. So it starts high, and then you can see that it starts decreasing steeply, but then as you get out here, it's still decreasing, but it's not going as quickly as it used to. For a lot of data like this, see if I can actually get it to work on here. So if I want to add a trend line, this is actually going to be exponential, or something that looks like exponential decay. And you can see the dashed line that's right there. So like out here, it's hitting most of the dots. Here, it's kind of overestimating. Here, it's underestimating. Out here, it's way, way off. But exponential decay looks a lot like that. If I do, just so we can see what I'm talking about here, we will do say concentration of whatever. This is going to be equal to the exponential value. So negative say 0.05, say times the time or speed here, something like that. Now if I graph, I'll try to graph this stuff on here. I can actually get both to go on the same plot. Have to do a right mouse click, select data. This time I'm going to add data. Series name is going to be this. The X values are going to be this particular column right here. The Y values are going to be this particular column right here. And you can see all of these are really small compared to what I had on there. But you can almost see kind of what's going on. I can remove that one. So there is my exponential decay. So it kind of does the same thing. Starts off big slope at the beginning, and then as you get further and further and further along here, it doesn't change nearly as much. How can you normally tell the difference between exponential decay like we have here versus the speed versus time thing that I have over there? Literally what I was just doing. You look at the data and go, that looks like it could be exponential. Try to fit an exponential function to it and see how well it works. It didn't work very well with the speed and time data. So I know speed and time are not exponential functions. With data like this, because I defined it as an exponential function, that's how it's going to work. But with the exponential, as well as with the speed versus time thing that we were looking at there, if you look at if we set up the concentration properly, so you can see at the beginning it's about 8. After about 20 minutes, it's about half as much. We can use information like that to figure out what's called a half-life for whatever this happens to be. Has anyone ever heard of a half-life before? A lot of times if you hear something about a half-life of a chemical, you're referring to nuclear decay of some kind. In the case of this, or in the case of something like this could be some nuclear decay, or this could also be how quickly does a patient or how quickly do you metabolize certain medications. When we look at medications, no matter what they are, there's going to be a certain concentration where if you go above that, it's toxic. Anyone here take a medication before and start to feel really, really weird? That means that you're basically taking too much of whatever that medication is, unless that's the way it's supposed to make you feel. Like a couple of weeks ago, I had a gout attack, and everything hurt, everything hurt, everything hurt. Went to uh, whatever whatever the clinic is, Beaumont Clinic, and they gave me a shot of something about half an hour later. Ooh, happy. All the pain is gone. I actually felt a little bit high, and I was happy. So, uh, was that, did they give me too much of the, cortisone shot, or is that just like, say the side effect of not feeling pain anymore, the body still can be producing all sorts of stuff to try to make, the pain stop? Or is it just, if I get high off of, uh, on my own, like pain relieving, sensation or chemicals and all that, you know. But anyway, What's gonna happen is, and above a certain concentration, you can get into some side effects. You can also get into toxic side effects. Below a certain concentration, the medication no longer has its original, say, medicinal use. So what you want to try to do is try to figure out how much can you give a patient, where do they stop feeling the effects of it, and then keep trying to dose that patient, bring them back up to whatever is an acceptable level, so that they can maintain, say, a functional life or not have any pain. Uh, about this time last year, I actually had surgery on my left arm. You might be able to still see the scar that's right there. They gave me all sorts of pain meds. I found that if I took one of their acetaminophen, said to one acetaminophen every 6 hours. Uh, at about 5.5 hours, I could feel the pain starting to come back. At 6 hours, it hurt like hell. Take acetaminophen. 20 minutes later, the pain's gone. About 5 hours after that, I could feel the pain coming back, coming back, coming back until it hurt. Take another acetaminophen, pain goes away. So that's exactly the type of thing that I'm talking about. At a certain concentration, you get the full effect without being toxic. At under a certain concentration, no longer has any effect. When it comes to different types of medication as well, uh, the body can adapt to how well it metabolizes certain things. Meaning, if it's the first time, uh, if I'm doing acetaminophen or something like that, uh, every 5 hours, 5.5 hours, and you could take another one to avoid pain. But if you acetaminophen too much, it might only last say 4 hours, get 3 hours, which would then mean one. If I'm supposed to take a pill once every 6 hours, but because I've been taking so much of it, it only lasts 3 hours. What do I do then? What's the thing most people would do? Take another one, right? Well, if you do that, you can again end up getting into that toxic range. You might not actually feel it until it's too late. Um, I don't remember what show I was watching, but they actually it's something that does come up quite often with the ibuprofen. If you take too much of it all at once, you can actually completely kill your liver and you need to have a liver transplant. And it can be something that you could do to yourself in as quickly as say a day or two. So, same thing with the acetaminophen and some other medications like that. Let's see, is there anything else that we need to worry about on here? So again, we're looking at the formula here. That's very similar to what we were just doing here, except I think my example is what would you call it? Useful, relevant. Don't you hate it when math is useful and relevant? I mean, seriously. So that actually does look like it's the end there. Let's see, is there anything else? All right. So this is like literally the same type of calculation that we just did. Anyone feel like Moladine anywhere? Anyone even know what Moladine is? And that's what I always used to do. So, walk, jog, bike, bus, car, jetpack. You can see that the speeds all change here. And what the assumption is here is that you're gonna be traveling that 40 miles. With the Excel sheet that I did here, we can actually change the distance that we're gonna be talking about. We can get it in time of hours as well as minutes. So again, how do we get it in time? In hours, I should say. You can see what's going on there. If we want to turn that into minutes, we literally have to take however many hours it is we're looking at, multiplied by 60. And think about the values up here too. 250 miles. If you're to travel west, how far can you get on 250 miles? Anybody know? So if you're going at an average speed of say 5 miles an hour, how fast is 5 miles an hour? Horse and buggy. Taking 50 hours to go 250 miles. If we so we are there. So 283 miles from here to Chicago. So horse and buggy at 5 miles an hour. How many hours is that? 50 hours. How many days traveling would that be? Because keep in mind, your horse needs to rest, your horse needs to eat, your horse needs to drink, right? And so do you. So 50 hours, if you do that, say 10 hours a day, uh, that would be what? 5 days to go from here to Chicago. Want to take a quick gas fly back in the old days, no one ever really went anywhere. If you, and keeping in mind the speeds that I've got on here too, this will be the last little bit for today. And I'll put this down to say 50 miles. Anybody know why, when we go to vote, it's usually gonna be on Tuesday? Unless it's a special election. What's so special about Tuesday? I mean, a lot of times, and again, back in the old days, if you were going to go vote, it wasn't a matter of saying you walk or drive or ride bike or whatever to say the local library, the local police station. You had to go, like say from here, you have to go all the way on. Let's say that's 25 miles away on average, let's say. So it's gonna take you uh 5 hours going at 5 miles an hour over your horse and buggy. That's basically back in those days, an entire day of travel. So why did we vote on Tuesday? Because you go to church on Sunday. Monday you travel, Tuesday you vote. Seriously. So just something to think about. Does anyone here take horse and buggy to travel from their house to go to the local polling station in Pontiac to vote? Yeah, no. Anyone here able to say walk from their house to their local polling station to go vote? Mine's like 2.5 blocks away, so I can do that no problem. So just something to think about. So why is it on Tuesday? Because of horses. No one uses horses anymore. Did we really need to have a voting on Tuesday? Well, now it's tradition, right? And that's all that I've got for today. I believe I've got to post the unit 4 tech assignments, or have I done that already? I don't even know anymore. Apparently I do things and then totally forget, and then other times I think I did things and didn't, and then get yelled at, why didn't you do this? So I guess I have to give you all the unit 4 tech assignments. I will work on updating grades uh, based on the last quiz and the homework and all that stuff that you've done online. So, any questions? All right. So I will see you all on Wednesday.